okay? Can you? Yeah, no. Right. So whether the magnetic field energy density is really stronger than that of the turbulence in the outer part is not completely clear. But even if so, we don't have to worry, because this is completely based on star formation turbulence, whereas, as I explained you, in the outer parts of the galaxy, there can be another source of turbulence, which is the MRI, the magnetorotational instability. So that could indicate that in the outer parts, the MRI contributes. But what is very clear is that magnetic energy density is 1 order of magnitude stronger than that of the ionized gas, and that means the plasma beta is 0.1, of the order of 0.1. So the interstellar medium is strongly magnetized and it's supersonic, and the ionized gas does not play dynamic any role. And this is really, it's not completely new, but it's not generally accepted to be the case. It's the thermal energy of the ionized gas. So just assuming temperature of 10 to the 7 and the electron density measured from H alpha. Right? So dynamical effects of magnetic fields have to be considered. I just mentioned 2 theoretical papers showing that really magnetic fields play a role. This is the star formation simulations by Price and Bate, a series of papers. And they showed that cloud fragmentation and star formation is really affected. So this is somewhat related to what I said in my previous talk, that magnetic field affects star formation, although we are not completely sure how. So these are different. Let me look at this again. So this is different m over phi's here. So this is m over. Let me look at that again myself. Don't remember myself now. So this is probably strongly magnetic, and yeah. So this is strongly magnetic case. This is a non-magnetic case, and you see that the cloud. This is a time sequence here for increasing magnetic field strength. The fragmentation of the cloud is slowed down, so it's much faster fragmented. And in case of non-magnetic fields, you get a double star in the cloud, whereas in the magnetic field case, strong magnetic field, you get only a single star. So the fragmentation of cloud is modified. There's less star formation for strong magnetic field, and there's a lower probability to get binary stars. And if you do this for many different models, the overall IMF, the intrinsic mass function, is changed. There are less low mass stars for strong magnetic fields. So this is a series of papers which I recommend to read, because they give quite clear results. A magnetic field change something. The other one is, it's especially for you now, the question of spiral arms again, by the same authors, by Dobbs and Price. They show that including magnetic fields, the formation of spiral arms is also modified. So this is a large beta, so big magnetic field. This is a strong beta, low beta, strong magnetic fields, and you see that the formation of spiral arms is really different. So spiral arms are much more fragmented, much more diffuse in case of weak fields, whereas magnetic fields seem to stabilize spiral arms and make them much smoother, much more straight, and just the magnetic pressure helps to confine spiral arms. So that clearly indicates that magnetic fields play a role in the evolution of galaxies. So these are just 2 examples. There are many more, but I thought these are the most impressive things to do. Another important effect of magnetic fields is concerning barred galaxies. So this is my beloved galaxy here, a barred galaxy in the southern sky here, and you see 1097. You can just observe it with a JVLA. It's a perfect southern object. So there's this very big bar. It's one of the largest bars known, and there's this very bright inner circumnuclear ring here, a strong ring of star formation. So this is an amazing object. This is a VLT picture, and you see that this is a star formation ring, and there's an AGN in the center, the Cipher type AGN. And this AGN is very bright. Bright AGN needs food, so you have to be fed. And how to get the gas into this AGN? It's not easy, because this is a star formation ring, and there's no reason for the gas to fall into the AGN. And there have been many papers with complicated triaxial potentials, bar within a bar or whatever, to explain how an AGN within a barred galaxy can be fed. And the answer is much more simple. Use magnetic fields. So magnetic fields do it for you easily. This equipartition field in that ring is very strong. It's of the order of 60 microgauss. And in addition to the turbulent field, which is connected to the star formation, you have also a spiral field. And so you have two effects here. You first have the Lorentz force of just the rotating gas, ionized gas, against the magnetic field, the turbulent field. And then you also have the spiral field, which is clearly inclined towards the circumnuclear ring. And both these effects give you a drag towards the center of the galaxy. Now this is quite simple. That comes from a classical paper of Balbus and Hawley, that the mass inflow rate depends on the product of the total field, and also the ordered field or regular field, and to take the averages here. So this is quite straightforward to compute. If you take the scale height of that disk of 100 parsecs, the velocity of 450 kilometers per second, you get the omega, the angular velocity, and then the field strength of the total and the regular field, you get a mass inflow rate of 1 solar mass per year. It's exactly what you need to feed the nucleus. So it's fundamental physics. It's just the Lorentz force. But for some reason, this is, although we published this in 2 different papers, it is not yet accepted by the community, because we are still thinking about triaxial potentials and all complicated gravitational things in that rings. Yes, it's different. This is no instability, it's just pure Lorentz force. I forgot to give the original citation. This is Balbus and Hawley. This is a review paper somewhere in the 90s where this is done for an accretion disk. So we just adopted that for accretion disk. This is done for accretion disk very easily. So you get a mass inflow, just pure Lorentz force, nothing else. Very straightforward. In Balbus and Hawley, it's a few lines in their paper. So it's simple. So magnetic fields are able to drive accretion. So big problem solved. Fine. So magnetic fields are sometimes very helpful. So to do this a bit more detail, you need MHD models, and unfortunately there is no 3D model, but at least there is a 2D model by Kim and Stone, 2012, and they show that indeed the formation of bars in nuclear rings are changed. This is a nuclear ring if you have different magnetic field strength, beta 1 to infinity. This is not important. This is an important one. So these are inflow rates here. So this black line is for no magnetic field, so beta infinity, and this is for beta 1. So the inflow rates are very strong. They are not reaching 1. Okay, in these models they are almost reaching 1. They are 1 solar mass per year, maybe a tenth of solar masses per year, but they are roughly consistent with what our simple estimate did. But this is without dynamo action. It's only turbulent field here, so 3D models are still pending. So they promised that they will do 3D, but I didn't see anything published on this yet. So MHD models seem to basically confirm this basic idea of magnetically driven accretion. Okay, so a few more examples why these spiral fields are important. This is an example of a ring galaxy, NGC 4636, done by Chris Ricci from Krakow. And you see, in spite of the fact that this is a ring galaxy, the magnetic field is spiral. So if there's a spiral, optical spiral, the dynamo cooperates with a density wave and with a spiral. But if a galaxy does not have a spiral, optical spiral, then it still forms a spiral. And this is an even more extreme case. It's a flocculent galaxy, and there's no spiral arm seen in optical and radio. There's still a spiral. So a dynamo always produces a spiral. If there is a spiral existing, there is some cooperation. If not, okay, then the dynamo just does whatever the dynamo wants, produces the spiral. There is a limit, as I said before. There is a threshold. If the galaxy gets too small and the rotation is too weak, like in a regular galaxy, IC10, then you're reaching the limit. Then you don't have spirals here anymore. They have some large-scale fields still, but is already getting weak. And the reason for that is probably the lack of differential rotation. So irregular galaxies, they cannot drive a dynamo, a large-scale dynamo. They still drive a small-scale dynamo, but no large-scale because they are rotating too slowly. Where the threshold exactly is, we still don't know. We have to find out. Okay, then coming back to what I mentioned already before, to the dynamo modes. So if the dynamo is really producing spirals, then we can look for these exosymmetric, bisymmetric patterns. So this is the exosymmetric one going in everywhere, or also vice versa, can go out everywhere. The bisymmetric does going in and go out. If you measure the Faraday rotation along the azimuth, you get a sine wave because of inclination, and you get a double sine wave because of inclination plus the reversal in case of the bisymmetric. And so on. A quadrisymmetric would then even higher modes. So if you do a simple Fourier analysis of your azimuthal variation of rotation measure, you can analyze the different modes you can find in a galaxy. And I mentioned that already. M31 is a classical case. It has a negative rotation measure here, positive there, so the field goes around, so it just runs around in a almost ring with a small pitch angle. So that was a breakthrough for a large-scale dynamo, but as I said, there's no other object as nice as this one. So this is another object which is relatively nice, so it has a positive rotation measures here and negative here. You start to see the effect of the turbulent field. So there's a lot of fluctuations. These fluctuations are not due to the measurement error. They are due to really variations in the field. But overall, there is still a field going inside here and also going inside here. But there are only these two magnetic arms, and our interpretation is the superposition of two dynamo modes, m equal to 0 and m equal to 2. I do a question mark here because we are not completely sure about that. But then there were also frustrations. So we observed M51. M51 is the nicest galaxy on the sky. It has a very nice spiral pattern. So we expected to see also a very nice pattern in Faraday rotation. And we were completely frustrated that is not the case. So in spite of the extremely nice spiral pattern and seen in polarization vectors, there's no pattern in rotation measure. How can that be? It should be the same field. You see in polarization patterns, you see the plane of the sky field. In rotation measure, you see the line of the sky along the line of sight field. Under some inclination, you should see the same pattern. We don't do that. Okay, we did not give up because we're believing in dynamos, so we did filtering away all the small-scale fluctuations, and then we found an underlying dynamo, m equal to 0 plus 2, but very weak one. What is dominating here are the fluctuations. And these fluctuations are still seen in polarization, but they don't produce any Faraday rotation. They produce zero mean Faraday rotation. And this is anisotropic fields. These are these fields in field loops, fields which are tangled, which are shared. And so the anisotropic field in this galaxy in M51 is several times stronger than the ordered field or the regular field produced by the dynamo. And the reason for that is probably because this has such a strong density wave, there's a lot of shear and compression. And shear and compression produces anisotropic field. And this happens on extremely small timescales. It happens almost immediately that the field lines are sheared or compressed, whereas the dynamo has always a long time to react on anything that's happening to the galaxy. So the local effects between the spiral arms, the dynamo has no chance to react on. There's an underlying pattern, but the actual Faraday rotation is much more complicated. So this is our interpretation. So there is an underlying m equal to 0 plus 2 mode. In the halo, we need another component, and there's possibly a bisymmetric mode in the halo. As I mentioned before, I'm personally quite skeptical about bisymmetric modes. You see going in, going out here, whether that can be excited. So I'm not sure whether this is an overinterpretation of the data. At least this is what we published in our 2011 paper. So there is possibly a reversal between the disk and halo. That's also something which is found in the Milky Way, but I should put a question mark after that. And then I mentioned already before, so the result of Marita Krause possibly a bisymmetric field, but the strong polarization in the interarm, where there are the neutral lines here, this speaks against the bisymmetric field, so that needs to be done again. And there are very strange cases, galaxies with only one reversal on one side of the galaxy. That's completely impossible. So if you plot the topology of the magnetic field here, you go round, 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 then it's rotated, so you cannot join the two vectors where they join at 180-degree jump. There's a 180-degree jump of the vectors here. It's impossible. So this is clearly showing the restrictions of a classical rotation measure analysis. So that needs RM synthesis. So that needs to be done with a new method. So obviously the classical rotation measure fails here completely. It's completely misleading here. So this reversal is absolutely odd. So sometimes it does not work at all. So we have to do this again. Somebody has to do this again. Okay, so summary of these dynamo modes. Axisymmetric modes are quite frequent. Bisymmetric ones are rare and possibly not existing. The magnetic arms can be described as a superposition of modes, but in many cases the field is more complicated. And if you want to read this in more detail, there is a nice review by Andrew Fletcher, who gives the list of galaxies, and he developed a method for this Fourier analysis of dynamo modes. You see the ground mode m equal to 0 exists almost everywhere. M81 is still exception. M equal to 1 is very rare. Sometimes it may exist there. And M equal to 2 is also existing. Sometimes all three modes are needed to explain the pattern of the magnetic fields. So this is a lot of work to do, and that's why the list of galaxies is still quite limited, and hopefully we can get more data on this. So to summarize the dynamo evidence, so dynamo has a lot of support. Magnetic and turbulent energy densities are similar. Spiral patterns exist almost everywhere. Large-scale regular fields do exist. Axisymmetric spiral fields, they dominate. Even parity fields dominate. I have no time to explain on this in detail. And as I explained before, there's no preference for one direction of the radial field. So there is almost as many inward as outwards. And this is also an indication that the dynamo really works. Okay, a bit more on detailed structure of magnetic fields. So this is the picture by Gene Parker. And so how the magnetic field should look like if you look from a side. So magnetic field is coupled in molecular clouds. So there the turbulent is excited. Of course, the field lines always have to close. So please let this line close somewhere outside. But then between the molecular clouds, there should be loops. And these are traditionally called Parker loops. And everybody believes that this is the reality, but there's very little evidence that these Parker loops do really exist. So if these exist, we should be able to see these loops here. And so there's one old example in M31, an old observation we made with a VLA. You see some wiggling of the vectors here. And at the same time, also the rotation measure shows the fluctuations. This is the general gradient you would expect, and around this gradient there are some fluctuations. So in 3D, in the plane of the sky and along the line of sight, there seems to be fluctuations, some periodic fluctuations. This is one of only two cases where we can see that. And the other case is NUC 6946, where George Shield found a small region in the galaxy where you see a plus and a minus Faraday rotation. That could be a loop going across. So why only one of them? So you can look everywhere else, is only finding this one here. So that's very strange. So if Faraday loops, you should see these features everywhere in a galaxy. So this Parker picture obviously has some problems. So obviously there's more going on in galaxies than just simple Parker loops. So sometimes they exist, but obviously they are quite rare. We don't know why. Edge-on galaxies. So dynamos need outflows. Without outflows, dynamos cannot operate. So if there are outflows, you would expect radio halos. And indeed, galaxies have radio halos. Very nice, bright radio halos. But the radio halos don't look like the dynamo predicts. The dynamo predicts dipolar or quadrupolar. Dipolar goes this way. Quadrupolar goes this way. So it has this pattern here. That's not what we observe. We see X-shaped. We see a completely different property of the magnetic field. So there's no dynamo can explain why there are X-shaped fields here. X-shapes are everywhere. So this is another X-shape here. That means the vertical component is not strongest near the rotation axis as expected from dynamo models, but it's obviously strongest away at large radii. So it's completely opposite to what we expect from simple dynamo models. So simple dynamo models are obviously too simple. We have to do something more. Quadrupolar field is certainly not the case here. Another X-shaped field you see going out here, very strong here on the southern part here. So that's obviously everywhere. So the halos are there. That's good news. So there's an outflow of magnetic fields, but the shape is not as expected. Another X-shape here. Now this is a very interesting case because this is a clearest case where you can see aging of electrons here. So we were very puzzled why the radio halo has this peanut shape here. So it's brightest and most extended in the outer parts here. So this was a complicated observation. We had 7 fields of the VLA. We had to combine that with Effelsberg, and this is an extremely tricky business. So I was not sure whether these depressions here on the both sides are real until we had a very simple idea. So the magnetic field strength is highest in the inner part and it decreases towards the outer part. So if electrons would move out here with a constant speed by a galactic wind, then they would lose their energy faster because the field strength is stronger here and less fast in the outer parts. It's simply because the lifetime of the cosmic ray electrons is shorter here than there. And indeed, we did this, and we plotted that the height of the halo against the lifetime of the electrons, and completely surprisingly, we could fit this with a simple line. So velocity is height over time, and we can get the velocity of the outflow in 300 kilometers per second. It works surprisingly well. So this is a direct measure of the outflow velocity of the cosmic rays in that galaxy. So amazing. So that can be applied to many other galaxies if we have the high enough resolution. So this galaxy is very nearby. It's the most nearby galaxy, nearby Edge-on galaxy on sky, but we are going to do this for many other galaxies. You can see the outflow also in the polarization vectors. You see that there's clearly this vertical field. There's also X-rays, which is green here. It's known since long. This is probably Rosot or Chandra, I don't remember, where you can see the outflow. And then we said, okay, let's look where the outflow is really coming from. So we did a higher resolution VLA observation, and then we saw this nice filaments here, which are obviously the edge of the outflow cone here. So this is the outflow cone seen in X-rays. This is now a Chandra image, and these filaments here are exactly at the edges here. So it seems that we can focus, we can analyze, we identify the outflow. The field strength in the outflow is really strong. It's more than 100 microgauss here. And more interesting, we could also measure the Faraday rotation. And across the outflow, the Faraday rotation jumps in its sign. And the jump in sign is most easily explained by a helical field in the outflow. So we can see the jump from one side of the outflow cone to the other side and can explain this by a helical field. So it's, I think, quite nice results. And a helical field can stabilize the outflow, can also confine and collimate the outflow. And this is maybe somewhat similar to the jets of radio galaxies. Okay, so summary of nearby galaxies. The ordered fields are of spiral shape. They are compressed in strong density waves, but they are also often concentrated in interarm regions. I had no time to mention this one, the polarization asymmetries. Just forget about that. Faraday rotation reveals large-scale fields, and there are no large-scale reversals found between spiral arms so far as for the Milky Way. So we don't find any cases like the Milky Way, which is puzzling. We should see them, the resolution is there, but we don't do so. So maybe our Milky Way is really special. Okay, just a brief remark on interacting galaxies. So interacting galaxies are extremely important because we learn how galaxies transform, and we can learn what happens to the star formation rate. This is the antenna galaxy here, 1048, 3839. And the strongest polarization, this is the polarized emission, is between the two galaxies in the region where there's still compression, but there's no star formation had yet started. So polarized emission can show you where the field is compressed even before star formation sets in. So that shows the earliest phases of the gas compression. And then star formation sets in much later. So that gives us a prediction of how this galaxy would look like. And just to show that there are first results about galaxy groups, and galaxy groups, especially for you, right? So that now there's indication that also intergalactic fields exist in galaxy groups, and there's also ordered fields in between here. This has recently been published by the Krakow group, and that gives indication that more groups need to be observed. So please go ahead and work on that. So the Virgo cluster has been studied already. There's not a group, but a big cluster of galaxies, and we found just a wealth of different structures. So every galaxy in the Virgo cluster is somehow different and shows something special. So there's offset of the polarized emission. This is a normal spiral galaxy. The polarization is completely offset. So this is really odd, and this is easiest to explain by ramp pressure. So that galaxy is moving through the intercluster medium, and the magnetic field is getting compressed on one side of the galaxy. Another galaxy has these big lobes here. That could be a tracer of past interaction. This is Effelsberg with a VLA. It's even more spectacular. You see these large loops here. So there is obviously a compressed region on that edge here. The galaxy is probably moving in that direction. So these outer parts here, they may indicate that there's something happened a billion years ago or even longer ago. So whatever you look, so we have published several atlas of many galaxies in the Virgo cluster. Every galaxy looks different, and every Virgo galaxy is a puzzle in its own. And Bernd Vollmer in Strasbourg in France, he's doing modeling to understand why the polarized emission is so different in different Virgo galaxies. Polarization is a clue to understand how interactions work in these galaxies. So in total emission, there's nothing special. In H1, you see interaction effects only over a limited time. In polarization, all these phenomena last for much longer, and they can be done much better. Okay, finally, what are the prospects for the future? So in for the future telescopes, we will be able to see distant galaxies, but even now, we are sometimes we're sometimes lucky to see distant galaxies. So this is an image which I got from Brian Gensler, and he uses that frequently in his talk. So it shows you the possibilities of Faraday depolarization. So this is Fornax A, observed with the VLA. This is the total emission. Now I switch on polarization. So it looks filamentary, lots of Faraday depolarization effects, and then there is a strange hole there. So if you zoom into this hole, there's a galaxy in this hole in front of this radio galaxy. So that galaxy depolarizes the emission of the background radio galaxy. So sometimes you should look for these holes, and you can find a really distant. I don't know what the redshift of that galaxy is, but it must be quite far away, because with radio galaxy observations, this Fornax, I have no idea how far that is. So that is one possibility. So with the SKA, we hopefully can observe galaxies to high redshifts. So why is this interesting? So I briefly come to the radio far-infrared correlation. So I briefly mentioned that the radio far-infrared correlation tells us the radio emission is connected to the star formation rate, but there should be a limitation for that, because the emission of cosmic ray electrons is not only going to the synchrotron range, to the radio range, but the energy of cosmic ray electrons can also go to the X-rays by interaction with photons. This is called the inverse Compton effect. And if you go to high redshifts, the inverse Compton effect against the CMB, the cosmic ray background, gets stronger and stronger. The photon field, the energy density of the photon field gets really strong. And beyond some redshift, most of the emission should go into the X-rays, and that means the radio emission should break down. And the radio-infrared ratio, that's the other way around, the infrared over radio ratio should go up. That means the infrared emission is still there, but the radio emission should decrease. So this is what simple models explain. These are different models for different field strength here, and these are what the observations tell us. So the ratio is more or less constant up to redshifts of roughly 5. That's how far we can observe. There may even be an indication that the radio emission even increases towards high redshifts. And that would mean that even the 500 microgauss is not sufficient, that these galaxies may have even milligauss fields to overcome the inverse Compton. So the equivalent magnetic field to inverse Compton is 3 microgauss times 1 plus z square. So to really have a dominating synchrotron emission and to preserve the radio far infrared correlation, the magnetic field strength has to be larger than this value. So at redshifts of 10, you would need, so this is 100, you need 300 microgauss to overcome that inverse Compton here, or even more. So going back in time and in redshift with the SKA, you can test that and you can trace the evolution of magnetic fields. You can measure the breakdown of the radio-infrared correlation, and by that measure how strong the magnetic fields are. So this is a very nice method which can be applied for the past. So can we really reach these high redshifts? Depends on the luminosity. So if a really bright galaxy, 10 to the 13 solar luminosities, with the SKA, these are the limitations for the SKA, these should be seen up to redshift of 10. So good news, but not all galaxies are as bright as that. So 10 to the 10, that's more a Milky Way galaxy. Okay, we can reach redshifts of 2. So starburst galaxies are somewhere in between. So somewhere of the range of 5, maybe up to 10, we will be able to detect with the SKA. Okay, 100 hours is a lot of time, but it's worth the effort, and that would tell us something about the evolution of galaxies in the distant universe. So I think I'm a bit early, leaving time for questions. The magnetic field observations with the new forthcoming telescopes is really opening up a golden age. So work with the SKA and work on magnetism. I think this is the right way to go. Thank you. Yeah, I think radio is clearly the best way to go. So what we need, we have to go back in time. We have to understand how galaxies evolve and how magnetism evolves. This is why one of the key question of the SKA Key Science project on magnetism is how did magnetism evolve in the universe? So exactly to find when did magnetism start to be important in the universe. And what I try to make clear is there are two sorts of magnetism. There's small-scale and large-scale magnetism. Small-scale, you would expect down to the very first galaxies. And large-scale, this is a crucial thing. So when exactly large-scale fields appeared in galaxies, this is a crucial point. And this is the crucial point to test dynamo. If we find large-scale fields already in very early galaxies at high redshift, then dynamo has a big problem, because the large-scale dynamo, you cannot do it faster than 10 to the 8 years, several 10 to the 8 years. It's impossible. You need several rotations to get all the polarities smeared out. So to combine to one single polarity needs several rotations. So that means you need probably 10 to the 9 years. And if we see magnetic fields earlier than that, then the large-scale dynamo has a big problem. This cannot be solved anymore. Okay, if we see large-scale fields later, okay, then dynamo is obviously even slower than. So that's a crucial experiment, and that is, I think the SKA is just the ideal instrument. On all other ones are not that useful. Yes, Rick. I have no idea. I was on a conference about AGNs, and I was proposing this, and I don't know. So maybe it's just the elephant in the room, and so that's so obvious, and they were all. There was no reaction on that. I have no idea why this is the case. It's just against their views or whatever the traditional views. I just have no idea on that. But clearly you're right. I think if people are not convinced yet, you have to do more. You have to do more things. I try to do a bit more, but the statistics is very bad. So what can be done is there is a relation between the star formation rate and the infrared luminosity of these nuclear regions. So that is an indirect evidence that indeed, so infrared luminosity is magnetic field strength, and so that is an indication that this may go in this direction, but it can also be interpreted in a different way. So I think we would need a larger sample of barred galaxies, and including polarization observations, and also measurements of the accretion rate. And this is so the luminosity of an AGN, and then determine accretion rate. So that needs probably a dedicated project to make this founded on a better base. So another project. So I don't have students to do that, but if somebody wants to do this, this is something you could really do important work. To convince this community is extremely hard. Huh? So it's like all standing around the elephant, and nobody is really daring to touch it and say, okay. And bulbous and holy are famous, so if you cite them, so then everybody should be impressed and say, okay, these are highly recommended scientists, and everybody would believe them, but still. So that's one of the examples with the elephant. Mm-hmm. Yes, there is a catalog, and in fact that gives me opportunity to make advertisement for this one. So before the book of this winter school is out, there is a chance to get all this information done. I've recently, with my previous boss, Professor Wilebinski, written a chapter for planets, stars, and stellar systems. Volume number, I don't remember, 5. And there we have a chapter on basically all what I told on my last lecture, and also about the Milky Way. So there's also a table of all observations which have been collected. So this is good news. Bad news is that this book costs $250. And again, good news, there's of course an AstroPH version of this one. So we were fighting with Springer, and they allowed us to put an AstroPH version on it. And the other good news is that I regularly update this paper. So there's already the 3rd version on that. So this table of observations is regularly updated. So every few months we observed more than 100 galaxies now. So we have in the Virgo cluster, we have already 30 or 40. There's a big list. So I would say that's 150 galaxies, maybe 200 has been observed. Oh, okay, well, but You need resolution. So statistics, of course, if you want to have total fluxes, this is a measure of total field strength. This is easy to do. But if you want to have detailed information about the polarization especially, then this is hard work. No? So every galaxy is an individual project. So if you look at the list of authors, there are authors, maybe 50 authors who have contributed to that list. Yes, these are a lot. So this is a radio-infrared correlation. So you can just look for these papers. So the radio-infrared correlation gives you total radio fluxes against infrared. So these catalogs are all available. So they are the total radio fluxes. They are easy to get. But this is somewhat boring. This relation is so tight. Now this is, you can use either the one or the other. So these are. Yes. Yes, but it also works within galaxies, but it's best studied for integrated values. So either luminosities, or in the past it was just radio flux, but now it is distance corrected, so they are radioluminosity against infrared luminosity. This is a classical correlation which has a slope of 1. If you go within galaxies, you can do it also within galaxies, then things get very complicated. So you have all sorts of slopes between 1.5, between 2 and 0.5, then it's really getting tricky. But if you ignore these details, then I think the overall properties like the total field strength, this is easy to get.
I would like to thank you for your very nice talk. And I'm going to thank you.
Welcome. Right. I think I showed you that the elephant is nice and useful and friendly.